Hi everyone, this lesson is on chapter 12, probability permutation. So this is day 2, so let's get started. Our learning targets are given a description of a desired permutation, find the probability of getting that permutation if an arrangement is already selected at random. So just also permutations, we're going to learn about what those are as well. So just a little warm up. Here we have these factorials where we have 20 factorial, 5 factorial. So I want you to be able to reduce that given this equation. So given 20 factorial, we're going to go 18 factorial is below that. So remember, when we write out 20 factorial, that's 20 times 19 times 18 and so on factorial, right? And then we have 5 times 4 times 3 times 2 times 1 all over 18 factorial, which is going to cancel 1 like that with the above 18 factorial in the numerator. And then we have 5 factorial, which is 120 minus 3 factorial. So we have 5 factorial right here minus 3 factorial. So I think that was actually meant to be 5 minus 3 factorial, but anyway, 5 factorial, which is 120, minus 3 factorial, which is 3 times 2 times 1, which is 6, right? So 120 minus 6. So 120 minus 6 is just going to be 114. And so what we have on top is we have 120, so that's that 5 factorial here, 120, and then we have times 20, and then times 19. So you guys can work that out. Let's see. I do have a calculator. Let me get that and fix that. And so what we have is 20 times 19 times 120 equals, divided by 114, it's 400. What I think, though, that this was meant to say was instead of 5 factorial minus 3 factorial, 5 minus 3 factorial. And if that had been the case, then we would have had, instead of this, we would have had 2 factorial on the denominator, which would be 2 times 1. And those values would have canceled out with this 2. And then we would have just had 20 times 19 times 5, or times 5 times 4 times 3. And that value was 22,800, as seen on the class slides, okay? 0 factorial is 1. How many ways can you write Thor? Now, this is pretty much what we're going to be doing today, where we're trying to find a shortcut to doing this. How many ways can we rewrite Thor? Of course. You can write Thor. You can write Torh. And so I would give you a few minutes to do this. And Tohr, Thro, and so on. So I would pause the video and go through and then come back and then say, how many times were there? Well, there was actually 24 different ways that I can rewrite the word Thor. Because after I do the T's, right, and there's actually 6 different ways that I could do that. I could go Trho, Troh, etc. There's like 6 different ways for each letter to start H, O, R, T, etc. So every time I would start with a different letter, I would have another 6 ways to rewrite that word. And so that ends up being 24 different ways. So this is kind of cool. This is what we're going to be doing today, dealing with permutations. So permutations. So for permutations, these are where the arrangement in the arrangement of objects is order matters. And that's really important that you understand the order of things matters. Just like when I was saying, how many ways can I rewrite the word Thor? There's 24 different ways. Now, if you think about it, what if I just had to rewrite it with the same letters? Well, I mean, that's not going to be the same thing. If order doesn't matter, then I could just, it doesn't matter how I rewrite that, right? It would be a little bit different. So with a permutation, the way I write ABC is different than the way I write CBA. So that means that order is going to matter, okay? So these are all the different ways that I could write ABC. So I could write it as ABC, ACB, BAC, BCA, CAB, and CBA. I have 1, 2, 3, 4, 5, 6 different ways. And that has to do with the number of values that I have, the number of letters that I have. So far, what we have is I had 3 letters, gave me an outcome of 6, okay? And if I, or actually 1, 2, 3, 4, 5, 6. If I had 4 letters, as in Thor, that gave me an outcome of 24. So if you're seeing a pattern, right, that's gonna help you with this. And we just did sequences and series. We actually could come up with a pattern. Where order matters, here's some examples: passwords, license plates, people standing on, depends on, like, phone numbers, especially phone numbers, because phone numbers are really tricky in that, like, you have the area code, right? Then you have the line number, and you cannot have certain letters or numbers in your area code, right? And they can't ever start with 0, etc. So, and then, like, the first number of your phone number also can't be 0 or can't be 1. So there's certain rules for phone numbers where order does matter. So we're going to get started with this. So we're going to talk about these permutations where order matters. And we're going to say, well, how many different ways could you arrange 3 books on a shelf? But you have 7 books to choose from. So we've got 3 different spots, right? So the first spot, the second spot, and the third spot. So in the first position, right, how many books do I have? I have 7 books. So I have 7 different options for the first problem, for the first space. But then once I've taken one of my books out, now I have 6 different options. And then I take that second book out, and now for the third spot, I only have 5. And every time I do this, and then I'm going to pick another one, and then I'm going to pick another one. And so what this ends up being is 7 times 6 times 5, right? And 6 times 5 being 30, 30 times 7, right? 210. So I've got 210 different ways that I could actually rearrange my 7 books in those 3 spots that I have available for my books. So a permutation is selected at random from the word sequoia. So what you need to do is you need to think of how many different letters do I have in the word sequoia. I've got SEQUOIA. Sequoia is actually kind of a cool word because it has so many different values. Does it have all of AEIOU? Sequoia actually has every vowel, other than Y, has every vowel that we have in the alphabet, right? It's kind of cool like that. A permutation is selected at random from the letter sequoia. What is now we're talking about a probability. What are my chances that Q is going to be in the 4th position? And it has to end with a vowel. So when you're thinking about this, you're thinking, well, sequoia has 7 letters. If I rearrange those 7 letters in any way, I'm going to get 7 factorial, right? So 7 times 6 times 5 times 4 times 3. Let's see, a little issue here. 4, and then 3, and then 2, and then 1. So that value, 7 factorial. And remember, definitely that you guys can also type this into your calculator. You absolutely want to be able to know how to use your calculator for this. And so when you're doing that, when you're putting this into your calculator, I'm going to show you how to do that. That's going to be 7 factorial. So we're going to go 7, and then you would go to math and go over to where it says probability. So 3 over to the left and 3 down, hit enter, 7 factorial. And so 7 factorial is going to give us 5,040. So that's how you would use, your calculator for that. So that's, what was that? I forgot. 7,040, 5,040, 5,040. Okay, so we have that value is 5,040. All right, so now we're going to set everything up and because when we find the probability, remember, that's the number of events happening over the total number of outcomes. And so first we're going to do is we're going to find, I want to select Q for the 4th position. So 1, 2, 3, 4. I only have one option for that. That has to be there. And then I want to select a vowel for the last position. So I've got 1, 2, 3, 4, 5 vowels. So I've got 5 options here, okay? And so now to find the other letters, right, I've used 2 letters up out of 7. So now I've used 2 letters up out of 7. So my remaining numbers are, I've got 5 letters left, but then I'll have 4, and then I'll have 3, and then I'll have 2, and then I'll have 1. And so when you multiply these all out, you end up getting 600. So that is the way, those are my permutations for rewriting the word sequoia. But they want to know the probability of this event happening. So the probability of this event happening is me taking my 600 out of 5,040 and dividing. So 5 divided by 42, which is 12%. Okay, cool. So a permutation, again, means I'm taking n objects r at a time. And what that means is basically very strongly, order matters, order matters, order matters. So important because when you're looking for the order of something happening, you just have to remember that not all events that come up, but some will matter. So order is going to definitely matter. So we'll see. Let's come up with some things. Oh, by the way, given this formula, NPR, this says n permutations of r. So this means the way you would find this is n factorial over, and then subtract the 2, n minus r factorial. And then again, of course, this is n objects taken r at a time. So our permutation formula. So I have 5 permutations of 3. That means I have sort of like our textbook problem where we had the 3 books on the shelf, right? But instead of having 7 books, I have 5. So we should get something like 5 for the first times 4 times the second, and then 3 choices for the last. And 5 times 4, which is 20, and then 20 times 3 is 60. So I should have 60 choices. So let's check. 5 permutations of 3 is the same thing as saying 5 factorial over 5 minus 3 factorial. So that's going to give me 5 times 4 times 3 times 2 times 1 over 5 minus 3, which is 2 factorial, so 2 times 1. 2's are going to cancel. I'm left with 5 times 4 times 3, again, which is 60. For this problem here, I've got 10 permutations of 8. So that's going to be 10 factorial over 10 minus 8 factorial. And so that's going to give me 10, times 9, times 8, times 7, times 6, times 5, times 4, times 3. And then the 2's are going to cancel, of course, times 1 over 10 minus 8, which is 2, factorial, which is 2 times 1. So the only 2 things that are going to cancel are the 2 times 1 and then the 2 times 1 again. So that number, I don't remember what that number is. It's pretty large, actually. I'm going to say maybe 1,814,400. I believe that's the answer for that. Okay? All right. So here we go with how a permutation might be used. So there's 12 players on the baseball team. All right. How many different batting orders can 9 people be formed? So you've got 12 players, but we can only have 9 people on the batting list. So we have 12 kids to choose from, but we're only going to select 9 because order matters. And so that's going to be 12 factorial over 12 minus 9. So 12 minus 9, parenthesis, factorial. So that's going to be 12, 11, 10, 9, 8, 7, and then 6, and then we have 5, and then 4, then 3, then 2, then 1, over 12 minus 9, which is 3 factorial, which is 3, and then 2, and then 1. So we cancel out the 3, 2, 1. That's 1 over 1. And we have 12 times 11 times 10, etc. And that ends up to be 79,833,600 choices those are the different ways that we can have the batting orders of 9 people out of 12 be formed. So for this problem here, this is like a lock. And I don't know if you've ever wondered this, but you know, when you're thinking of a lock and you're thinking, well, I have 35 numbers on the lock to choose from. And let's say that I can only select 3. So how many different codes can I have? And I see that this particular lock actually has more than 35, so we're going to ignore that part. So let's just say it's 35 and I only have 3. So, oops. So those are the 3 options that I have. Let me fix that. So we have 1, 2, 3. So the first time we go to select the number, assuming that there's only 35, is I have 35 options. And then the second time that I choose that, right, is going to be now I have 34 numbers to choose from, assuming that I cannot use the same number again. Because otherwise, if I can use the same number again, then order wouldn't necessarily matter, and I could just go 35, 35, 35. So 35 times 34 and then times 33, that ends up to be about 39,270. Okay, now assuming that this is the way that the order matters, I can't use the same number, what's going to happen then is another option of writing this is 35 permutations of 3. So the way you would write that is you'd go 35 factorial over 35 minus 3 factorial. So it would be 35 times 34 times 33 times 32, you know, and this is factorial because that's just going to keep going on. And 35 minus 3 is 32 factorial, right? So that is actually going to replace that. So this 32 factorial will cancel with that with the numerator and the denominator, leaving me with 35 times 34 times 33, which, if you can see up at the top, that's the same thing. So you have an option of writing it this way. It just can get sort of tedious. And by the way, your calculator will multiply those permutations out and combinations out when we get to the next value of combinations. Okay, so when I want to rewrite, like we were dealing with the word sequoia, how many different ways can I rewrite this word marvel, right? Just pretend like I don't have any repeating, just like sequoia. How many different ways could we have written sequoia, right? That was 7 different letters. I had 7 options, so that's 7 factorial. Likewise, we've got 1, 2, 3, 4, 5, 6. 6 options, 6 factorial. That's going to give me 6 times 5 times 4 times 3 times 2 times 1. And so basically, if you think about it, that's going to be, if you worked it all out, you're thinking that's going to be 5 times 4 times 3 times 2 times 1 is 120. So if I just took 120 and I multiplied by 6, right, I'm going to get 720. So there's 720 ways that I could rewrite the letters of Marvel, and I can rearrange them. But if you think about it, is what if some of my letters are repeating? Okay, so that's what you have to think about, is what happens when my letters repeat. And what that means is that because that's what that is that's going to be where order matters. So we have to think about, what if we think of the word Spartans, right? We've got 1, 2, 3, 4, 5, 6, 7, 8 letters. So we know that we have 8 factorial ways of rewriting Spartan. But when you think about that, you have to ask yourself, are there any letters that are repeating or used more than once? So for example, we have 2 A's. So we have 2 A's. And also, it looks like I have 2 S's. Also 2 S's. Okay, and so what that means, so we've got 2 S's. Is there any other letters? I don't think so. Okay, so what you would do then is you're going to divide out those repeating values. So those repeaters, we're going to say, well, there's 2 A's and there's 2 S's. And so now, when I write this out, I have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 2 times 1 times 2 times 1. So if I work that out, that's 4, right? I'm going to cancel out my 4. And so what I have now is just 8 times 7 times 6 times 5 times 3 times 2 times 1, which ends up to be about 10,080. And so that's how many non-distinguishable, how many letters that are distinguishable can be arranged in the word Spartans, okay, if order matters. So for a set of n objects in which n are one of a kind, so this is my formula. So this is what they're saying. Hey, n values, if I have any repeaters, I have to divide those out. Okay, so when you think about the word Mississippi, and you think, well, I've got 11 different letters in the word Mississippi, so I've got 11 factorial. But if I want to arrange these, and I've got to think about, hey, order matters, but I have repeating letters. So I'm going to toss those, that's going to make a difference. And so when you think about it, it looks like you've got 4 I's, you've got 4 S's, and 2 P's. And so therefore, we have to divide out our 4 factorial, 2 factorial. Okay, we are to divide out all our repeaters. We end up getting about 34,650 different ways that the letters in the word Mississippi that are distinguishable can be rearranged. Calculus, we have how many different letters? We've got 1, 2, 3, 4, 5, 6, 7, 8 factorial. We have 2 C's, so 2 C's. We have 1, 2 U's. And we have 2 L's. And so this 8 factorial would be divided by 2 factorial times 2 factorial times 2 factorial. And, yes, you can just work this out and multiply 8 times 5, whoops, 8 times 7 times 6 times 5, etc. 8 times 7 times 6 times 5 times 4, 3, and then 2, and then 1. And those 2 times 2 is 4 times 2 is 8. Those values, I'm going to knock that out with the denominator, and now I just have this left, which is basically 6 factorial, right, which we know is 720. And then 720 times 7 is what? 5,040. And so those are how many different ways that the letters of the word calculus can be arranged. Done. So here we have one of my good students, Frantic, takes a 10-minute problem, Algebra 2 test. And this test, it's an honors test, so they have to work very hard. These problems can be worked in any order, but they're wondering how many orders could Frantic work all 10 problems. So that is just going to give you a 10 factorial, okay? And that ends up to be like 3,628,800. So that's how many different ways we can work all 10 problems. But if I only want to do 7, let's say Frantic is like Frantic, and I can only do 7 problems. So of the 10, we have 10 permutations of 7. And so therefore, we would go 10 factorial over 10 minus 7, which is 3 factorial. Cancel those values out. And I believe you get like 600,000, 604,000, something like that. And that's how many different ways Frantic can do 7 out of the 10 problems, in her particular order. And this is, if the first part, though, I want to be very clear. If this is the case, she can do them in any order. That's 10 factorial because there's no restrictions there. Now, let's suppose we have Deadpool license plates. Wouldn't that be awesome? And they are made using exactly 5 of the 26 letters in the alphabet. So how many different ways so can be used if all, we're going to say 5 letters are different. So if all 5 letters are different, so we're thinking about 1, 2, 3, 4, 5 letters in the alphabet. You got 5 spaces for your words. And when you're doing that, you've got, let's see, how many different Deadpool plates can be used? If the letters could be any letters and that they could be repeating, we would have 26 times 26 times 26, etc. But because the letters cannot be used again, they're all different, okay? Therefore, we have 26 choices for the first letter. And then once we use one letter of the alphabet, the next one is, and then 25. and then 24, and then 23, and then 22. This is going to be the same thing as you saying 26 permutations of 5, because the order will matter because you can't use the same letter more than once. Doing this, you end up getting, I think, I don't remember, I want to say 7 million or more than that. So you guys can work this out, okay? So now we have the Mountain View parking lot has 3 spaces for that are labeled AP. However, there are 7 APs at school at any time, right? And so how many ways can our 3 parking spots be arranged with those 7 APs? So that would be 7 permutations of 3. And so basically you could say 7 options here, and then you have 6 options here, and then you have 5 options here, right? So just 7 times 6 times 5, also the same answer for that. And that's, I think, 210, something like that, okay? For baseball, again, now this is a little bit different. We have 9 different people trying out for 9 positions on the baseball team. How many different ways could those positions be filled? There's no restrictions, so order doesn't matter. In this case, we have 9 factorial, okay? So we basically have 362,880 choices to choose of these baseball players on the baseball team. So in how many ways could the positions be filled if Nicholas, who's playing baseball, must be the pitcher? So, and then we have 9 kids altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nicholas has to be the pitcher, so there's only 1 option for that person right there. But then the rest of the kids, we've already used 1 kid out of the 9. So now I only have 8 left. So it's 8, then 7, then 6, and then 5, and then 4, and then 3, and then 2, and then 1. If the positions, though, are selected at random, what would be the probability that Nicholas, and it looks like we spelled his name differently here now, will be the pitcher? So the probability would be this value here, which turns out to be about 40,320. It would be 40,320 out of 362,880. Dividing that out, you end up getting like 1/9, which turns out to be about 11%. So that's the probability that Nicholas would be selected the pitcher. So what we have here are the letters ONG, GONNGO. I feel like I'm singing Benji. Okay, so what we have here are the letters of a triangle. And you think of like how many different ways can we rewrite this triangle with different letters, right? And you think if not just using the letters, of course, ONG, NGO, or GNO, if I used any letters of the triangle, how many different options do I have? And so you think about it like this, is you think, well, what does your teacher do, right? When she teaches geometry, he or she teaches geometry, and they're thinking, well, I have, how many different letters do I have to choose from? I've got 26 letters. And then the second letter, of course, I'm not going to use the same letter. That would be 25. And then, of course, you're not going to say ONN, because when you ask for angle N, you don't know which angle you're using. So 26, then 25, and then 24, that ends up to be about 15,600 options that your teacher, geometry, or whoever's teaching you at that time, has to pick those letters. 15,000 choices. Crazy. All right, so here we go. We have Max, Matthew, and Maurizio are all drawing 2 cards from a normal deck of 52 cards. But the trick is that they're not going to replace them. Max is going to go first. It says, how many orders can Max draw as 2 cards? So he's going to have 2 cards like this, 1, 2. The first choice he has, the first option is he has 52 cards. And he can't replace them. So his next pick is, or draw, is going to be, he has 51 options. So now he has, 2,652 chances or orders of drawing his 2 cards. But then after Max is done, then there's Matthew, and Matthew's going to draw 2 cards also, but 2 cards are already gone. So now Matthew has 50 and then 49. And so that is going to be 2,450. And then Maurizio is going to go after Max and Matthew. And so they've already used 4 of the cards. So for Maurizio's, he has 48 cards to choose from and now 47. And so his options are now what? 22,050, oh no, 6? Yeah, something like that. And so that's how many orders that he could choose to draw his 2 cards. So here we go with this permutation. This is the letters from the word great, not G-R-E-A-T, which is down here, but we're talking about the letters from the word great as in G-R-A-T-E, okay? So if I'm thinking of the words from great, the letters from the 5-letter permutation selected at random, for the letters of the word great, G-R-A-T-E, how many permutations are possible when order does not matter, okay? There's 5 letters to choose from. They're all different, no repeating. That's going to be 5 factorial, which we know now is 120. How many of these permutations, though, would actually begin with the letter G? So you have to think, I've got the 5 letters, 2, 3, 4, 5. G, if I want G to start, there's only one option for that. And then the rest of the ones, I don't care. It's just G has to be in the beginning. So then I've already used up 1 letter, so now I have 4 letters left, and then 3, and then 2, and then 1. So I now have 24 different ways I can write those 4 letters, right? And that are remaining. Sort of like the word Thor when we started, and we had 24 different ways we could write that. Now, what is the probability that the permutation begins with G? So every time they say the probability, we are going to take that value, probability 24, out of the event happening out of the total number of outcomes, which is 120, and reduce that, you get 1/5. Next, we want to know what is the percent probability. Well, you just divide 1 divided by 5. That's 0.2, which is actually 20%. And lastly, I want to know what is the probability that permutation is actually great. So like spelt like that, which is the same letters when you think about it, but these 2 letters are flipped around. So we have our 5 letters, 3, 4, 5. And so it's just 1. The probability is just 1 out of 120. Because remember, if this letter has to be G, there's 1 option. If this letter has to be R, there's 1 option. If this letter is E and then A and then T, 1 option and then 1 option and then 1 option, you just multiply those out, you get 1. And if they're asking for the probability, it's out of our total outcomes, which is 120. So 1 out of 120 is like 80 point, what is that, 0.83%? Yep, 0.83%, I think. Okay, so that's pretty neat. Okay, all right. So given a description of a desired permutation, we did find the probability. We also learned about permutations and their very cool formula NPR, which is n factorial over n minus r factorial. And this is about segment or arrangements selected. Tonight's homework is permutations. So get started on that. You have odd problems. Wishing you a great rest of your day. Thanks for watching.